Hello, scholars. We've covered quite a few logical fallacies. There are a couple more that I want to talk about, and those relate to the questionable use of statistics. Perhaps you've heard this saying, sometimes attributed to Mark Twain, although he was quoting someone else. There are three kinds of lies: lies, damn lies, and statistics. Now, what this quote says pretty clearly is that statistics can be used to tell lies. They can manipulate the truth and make us believe things that aren't actually true. Now, I think it behooves us all to be aware of ways that statistics can be misused and misrepresented. But I do want to point out here that as we think about this, there's a need to find a balance. On the one hand, we need a healthy skepticism when we're presented with numbers, with data, with charts, with graphs. We need to be willing to question those numbers and to do research if it's a matter that concerns us. We need to check it out before we pass it on for someone else's consumption. On the other hand, I don't think we need to become conspiracy theories, nor do we need to fall in the trap of rejecting any kind of data or number that supports something that we disagree with. Sometimes we need data to tell us hard truths about how we need to be living our lives or about conditions that exist in the world. So we respect data, and we understand that good data can lead to better outcomes. And our goal, as we try to figure out the best ways to live our lives, the best food to eat, the best candidate to vote for, our goal again should be to find good data and good information. Now let's cover just a few ways that statistics can be manipulated and used fallaciously. All right, first, cherry picking. If you went to go pick fruit, you'd be looking for the good stuff, right? And you'd be tossing the bad stuff. But you don't want to do that with your data. Cherry picking is including results that support what you want people to believe and leaving out the stuff that doesn't. So let's say you're a drug company, you've developed a great drug that really helps relieve pain, but you happen to find that has a side effect of causing serious addiction. If you only present to the doctors you're trying to sell this drug to the information about how well it relieves pain and leave out the stuff about addiction, then you're not just being irresponsible, you're being kind of evil, right? Cherry picking is not good. Now, when you become scientists, I hope you'll learn all about data dredging. Here's my little baby introduction here. Okay, data dredging is misusing data to find patterns that look significant, but that are the result of chance. So here's an example that I talked about briefly if you had me last year. Imagine you want to find out the effects of dark chocolate on health. So you get a group of people, you have them eat dark chocolate for a month. And at the beginning and at the end of the month, you test just a whole bunch of things. You test their weight, their cholesterol, how well they're sleeping, their happiness level, their liver condition, who knows what, right? You test everything. And it's highly likely that if you're checking that many things, that by chance, one of those things will fluctuate over the course of the month in a way that looks significant. Now, is that a result of chocolate? No, again, it'd probably be the result of chance, right? This is kind of like taking a big handful of dice and tossing them, hoping that at least one of them comes up number 6. And the more things you test for, the more chance it is, again, that you're going to get lucky. Now that relates to good scientific design, but more of us should become scientists. Okay, now when we look at data, it's important to pay attention not just to the data that we have, but to the data that we don't have. So survivorship bias is focusing on data that has made it past some selection process, but ignoring the data that hasn't. So again, we need to think about the information we have, but also the information that we don't have. So here's an example that I read of this. In World War II, when they were trying to decide what kind of armor to put on planes, they were looking at the planes that had come back from battles, and they were noticing bullet holes on the wings and over the plane, but no bullets in the cockpit and no bullets in the engines. Now, if you look and say, well, we've got no bullets in the cockpit or the engines, it'd be easy to think, well, those places don't need to be protected, right? On the other hand, you think about the information you don't have. Well, the planes that didn't make it back were probably the ones that got hit in the engine or hit in the cockpit. So focusing on the information that you don't have there would let you know the better places to put armor on those planes. Now, false causality, we've talked about this before. This is the correlation equals causation fallacy, or it's the post hoc fallacy, the idea that because two things are related or that because one occurred after the other, that one must have caused the other. So think about it. At certain times of the year, we have more people consuming ice cream, and then we also have more people dying in swimming pools. Do we say that consuming ice cream causes drowning deaths? Well, no, we'd say that there's a third cause, and that's the hot weather that causes both. So sometimes you got to be careful about assuming that one thing caused another. I included a link to the article that I got this graphic from in the course and the materials for the last round of logical fallacies, but it gives me a laugh every time I look at it, so I thought I'd put a few of these graphs here for you. You can see there's a strong correlation between Internet Explorer use and the murder rate. And I gotta say, guys, it is a good thing that more of us are using Chrome. Or how about this one? Did you know that M. Night Shyamalan makes bad movies because people don't buy newspapers? Gerrymandering you probably talked about in your government class. It's manipulating political borders to sway election results. So if you take a look at the graph there, imagine that we have an area that needs to be drawn into districts, and some of the precincts are yellow and some are green. Depending on how we draw those boundaries, we can either make it so that yellow wins all, or we can make it so the green wins the majority. Or we can try and draw in a way where we get, proportionate outcomes. Now, sampling bias, imagine you go to a dog show and you ask the people there whether they prefer cats or dogs. Well, probably at a dog show, most of them are going to prefer dogs, right? So if we are simply talking about dog owners preferring dogs, that would make sense. But if we try and take those results and generalize to, say, the country as a whole and say 90% of people prefer dogs to cats, then that would be an unfair sampling bias. Or if I, as a teacher, were to ask my 5 top students how easy the material is and then base my lesson plans on their results, that would be bad sampling bias too. Another issue is small sample size. This is hugely important because if you don't have a big enough sample, you can't be sure that the conclusions you're drawing are representative of real truths or whether they're just random chance. So let's say we just want to find out what the average height of people in America is. If we get a large group of people, there'll be some really tall people, some really short people, and a bunch of people in the middle. Well, the tall people and the short people will balance out, and we could find a pretty true average. On the other hand, if we just take a small group, we might randomly happen to get a couple of really tall people in that group, and that will skew the average up. Or we might happen to get a couple of really small people in that group, and that would skew the average down. So again, in order to avoid the random chance of having someone exceptional in our group, we need to measure the heights of lots and lots of people. Now, there are plenty of problems that come along with small sample sizes and misinterpreting results. So if I told you that rural counties have the lowest rates of kidney cancer, you might look at that and say, well, it's that good, clean living, it's working outdoors on the farm. But I might also tell you, and it would be true, that rural counties have the highest rates of kidney cancer. So you say, well, how can rural counties have the highest rates and the lowest rates? Well, it's because rural counties tend to be smaller. There are fewer people. So in one county, you might randomly happen to have a couple more people with kidney cancer, and that would skew your average up. And then in another county, you might happen to just randomly have more people who don't get kidney cancer, and that would skew your results down. So again, it's always worth asking, how many people respond to the poll? How many people did you test? How many people did you survey? And if that number's not big, then you should be skeptical of the results. Now, we talk about regression towards the mean. We're talking about things sort of returning to the average, and mean here means average. So when something's exceptionally good or bad, over time it tends to go back towards the average. Imagine that I gave 100 students a multiple or a true-false test, and they didn't know any of the answers. They were randomly guessing. Well, most people would randomly guess, and they'd earn about a 50%, right? But there'd be a couple of people who would randomly guess lucky, and maybe they'd earn like a 90%. And there'd be a couple of people who'd randomly guess really poorly, and they'd earn like say a 20%. Now, if we were to give that test again, what's the chance that those people who randomly tested high would randomly test high again? Well, it's kind of unlikely. They're more likely to move closer to getting 50% right and 50% wrong. Now, it's just the natural tendency of things to sort of move towards average. So when we see results changing, we should say, is this because something really did change? Or again, we did just have some random results that are now becoming more average? Finally, let's talk about the McNamara fallacy. This is named after Robert McNamara, who during the Vietnam War measured success in terms of body count. So he's making his decisions based on things that he could count instead of other considerations. Body count is not the only measure of success in a war. You have to take into account people's attitudes, the morality of what you're doing. Again, there may be things that are less easy to quantify, but that matter. So let me emphasize again here that we need to find that balance between having a healthy skepticism when we're confronted by numbers, asking questions like who was polled, how many people were polled, is there other data that got left out, having that willingness to question numbers, but at the same time respecting that data helps us make good decisions and that correct use of good data can lead to better outcomes. Take that statistics class.